Beneath the waves of the Baltic, engineers are building a tunnel so vast it will swallow 18 kilometers of sea, each section heavier than the Eiffel Tower, cast in a factory bigger than some towns. This isn't a futuristic sketch. It's real, underway, and poised to connect Denmark and Germany in under 10 minutes. But why did they choose the riskiest tunneling method on Earth? And what could go wrong when you try to assemble a highway and a railway underwater using 89 concrete giants? The answers reveal just how insane this project truly is. Immersed tube tunnel construction begins not with a drill, but with a blueprint for assembling colossal concrete sections, each one built on land and then placed underwater with surgical precision. Instead of boring through rock like a traditional tunnel boring machine, this method relies on prefabricated elements, sealed and floated out to sea like enormous ships. Once in position, each segment is lowered into a trench dredged along the seabed, then joined and sealed to its neighbor, forming a continuous watertight passage. This approach is not new, but its scale here is unprecedented. Earlier projects proved the concept. The Øresund-Drogden Tunnel, linking Denmark and Sweden, stretches about 4 kilometers beneath the strait, its elements cast and sunk in a similar way. In Istanbul, the Marmaray Tunnel crosses under the Bosphorus, its 1.1-kilometer immersed section engineered to withstand earthquakes and relentless currents. Both projects pioneered techniques for sealing joints and aligning segments, but neither attempted anything close to the scale now underway in the Baltic. The Fehmarnbelt Tunnel pushes this technology to a new level, nearly 18 kilometers long, with elements more than twice the length and weight of any before. The soft seabed of the Baltic ruled out deep rock tunneling, and the busy shipping lanes demanded a solution that could be built with minimal disruption above. By industrializing the process, casting, curing, and assembling these massive segments in a purpose-built factory, engineers can control quality and speed in a way that was never possible before. This is not just a tunnel, it is a leap in how infrastructure can be built beneath the sea. Inside the sprawling industrial complex at Rødbyhavn, construction moves with the rhythm of a factory floor rather than a traditional building site. 6 massive production lines stretch across 3 climate-controlled halls, each one dedicated to shaping the backbone of the tunnel, giant concrete elements measuring 217 meters in length and weighing over 73,000 tons apiece. These elements are not poured in a single effort, but assembled from 9 segments, each about the size of a city bus, reinforced with enough steel to rival the Eiffel Tower, multiplied 50 times for the entire project. The process begins with automated welding robots in the panel factory, cutting and shaping steel coils into intricate reinforcement panels. Every week, these robots handle up to 400 tons of steel, feeding a steady supply of skeletons to the assembly lines. Workers position the panels in casting pits, surrounded by hydraulic formwork and skidding beams coated with epoxy, ready for the next phase. Concrete is mixed in 2 dedicated batching plants, delivering up to 600 cubic meters per hour through a network of booms. Each segment is cast in a continuous pour lasting 30 to 36 hours, ensuring seamless strength and durability. Once the concrete cures at a steady 20 degrees Celsius, the formwork is stripped away and hydraulic arms inch the finished segment forward, making room for the next. At full speed, the factory aims for a new segment from each line every week, producing a complete tunnel element every 9 to 10 weeks, an industrial cadence that transforms raw materials into colossal building blocks, ready for their journey beneath the Baltic Sea. Out on the Baltic, the choreography begins long before sunrise. Marine crews gather at control stations, scanning live feeds and weather reports. The seabed trench, stretching nearly 18 kilometers, is already carved by dredgers. its base lined with gravel and rock for a perfectly level foundation. Each tunnel element, sealed at both ends with steel bulkheads, floats in the harbor basin, holding enough air to counteract its weight of 73,000 tons. Tugs nudge the element into open water, guided by GPS and acoustic beacons. On the bridge, the Marine Operations Lead calls out adjustments as cables and winches hold the element steady against wind and current. Every meter counts. The alignment window is measured in centimeters, and the rotation must fall within a fraction of a degree. Once the position is locked, ballast tanks flood in a controlled sequence. The element sinks slow and even, watched from above and below by divers and engineers. Hydraulic jacks and fine-tuned sensors track its descent, correcting for drift in real time. When the element settles onto the seabed, teams move in to connect it to its neighbor, compressing joint gaskets and sealing the seam. Grout is injected, and armored rock is poured over the tunnel for protection. Behind the scenes, control rooms monitor every parameter from pressure to tilt as the next element waits in the harbor. The entire sequence repeats day after day until the tunnel stretches unbroken beneath the Baltic Sea. Pressure at the tunnel's deepest points reaches 3 atmospheres, enough to crush a car in seconds if anything fails. Every joint must resist that force for over a century. Sealing a pair of 217-meter concrete giants underwater demands more than brute strength. It requires a system of EPDM gaskets, each custom molded for the Fehmarnbelt's unique clay and shifting seabed. These gaskets, known as Gina and Omega seals, are compressed by hydraulic jacks, then tested with pressurized water to verify water tightness before grout is injected to lock the seam. Quality assurance technicians run concrete cube tests, permeability checks, and ultrasonic scans on every segment, logging results in real time. Failures trigger immediate rework. There is no room for error at this scale. Once an element is in place, a network of fiber optic sensors buried inside the concrete comes online. These strands measure strain, temperature, and even micro movements as the tunnel settles. In the control room, the chief engineer and her team watch dashboards streaming live data from every element: pressure spikes, joint compression, and alignment drift. If a reading strays beyond tolerance, alarms sound and teams mobilize, whether it is a misaligned segment or a sudden storm above. Weather windows are tight, and vessel delays can push immersion by weeks, as happened during the Ivy prototype trials. But every risk is mapped, measured, and managed. The system is designed to catch the smallest anomaly before it becomes a threat, building trust in a structure meant to outlast generations. Shift change sweeps through the tunnel village as the clock hits midnight. Nearly 1,300 workers keep the Fehmarnbelt project moving, their routines as tightly choreographed as the machinery they oversee. In the panel factory, a foreperson inspects the output of robotic welders, checking each steel panel for perfect alignment before it moves down the line. Outside, a skipper briefs his marine crew, reviewing weather data and vessel checklists, knowing that a sudden squall could halt towing operations for days. Inside the casting halls, teams pour concrete by the ton, working in 12-hour shifts to keep the assembly lines running day and night. Cafeterias serve hot meals around the clock, and dorms fill as one shift ends and another begins. Routine tasks such as testing concrete samples, monitoring sensor dashboards, and calibrating cranes are repeated with unwavering focus, each step logged and verified. The scale is industrial, but the effort is personal. Every segment owes its precision to hands and eyes on the ground, working in sync with machines built for endurance. Deep beneath the Baltic, the tunnel interior unfolds as a network of precision-engineered spaces. 2 parallel road tubes, each carrying 2 lanes of traffic, run beside a separate rail tube built for high-speed electrified trains. Between them, special service elements house emergency exits, ventilation systems, and the pumps and sensors that keep the tunnel safe. This is not a single cavern. It is a series of corridors, each designed for a specific flow of people, vehicles, or data. Every standard element is 217 meters long and locks into the next to form an unbroken passage nearly 18 kilometers from Denmark to Germany. When finished, a train will cross the Fehmarnbelt in just 7 minutes, replacing a ferry trip that can take an hour or more. For drivers, the journey between Scandinavia and continental Europe will become as simple as a highway merge. By 2029, this shortcut will reshape travel and trade across northern Europe, turning what was once a maritime boundary into a seamless link. Right now, 89 colossal tunnel segments wait in Danish harbors, concrete proof that Europe is reshaping its borders beneath the sea. Once opened, this link will cut travel times and redraw economic maps for millions. Progress is not just above ground anymore, it flows deep and silent beneath the waves.